We have previously discussed about the actinides, their production, some of the actinides, their discovery, and also their electronic configuration. Now, as I've already mentioned before, the actinides have a relevance in the nuclear fuel cycle. So we need to understand the chemistry of actinides, particularly those which are relevant for the nuclear fuel cycle. So in this lecture, I'll be discussing about the chemistry of uranium to americium. That means uranium, neptunium, plutonium, and americium. These four elements mainly, they have great relevance in the nuclear fuel cycle. Other details will be covered in separate lectures. This lecture is just a broad chemistry of uranium to americium. Now, when we are talking about the chemistry of actinides, we also should know about their complexation, that is, the interaction of actinide ions with the ligands, which are mostly Lewis-based. The interaction with actinides are mainly electrostatic, that is, ion-ion or ion dipole. So all the actinide metal ions are ions, and we have the ligands which can be neutral ligand. In such case, we have an ion dipole interaction. And if it is an anionic ligand, then it is the ion-ion interaction. Now, this interaction energy is a measure of the stability constant, and it is proportional to the charge on the metal ion, and also inversely proportional to the distance between the ions. I have shown some schematic here in which the different actinide ions are represented by either plus or plus plus, that is multiple charged metal ions, and the ligand, for simplicity, I have taken just minus for all cases. Now I have taken 4 cases where the metal ion size, I've also tried to show the size of the metal ion. The first case, the size of the metal ion is bigger than that of the second one, where the size is smaller. And in case of the third one, the ligand size is bigger than that of the metal ion. And also in the fourth case, we have the doubly charged metal ion, which has a bigger size than that of the donor group of the ligand. As you can see, the radius between the metal ion and the ligating ion is varying depending on the size of the metal ion. So now, as I have mentioned, the stability of the metal complexes will depend not only on the charge but also the distance between the ions. Now, actinides, as we know that they are from actinium to lawrencium. Now, this size of the actinides, when we take a particular ionic species, say +3 oxidation state, then the size of the actinides will be changing. This phenomena is called the actinide contraction, that is, the ionic radii decreases with increasing the charge of the actinide ions. Now, this is similar to the lanthanide contraction, and it has a great significance in the complexation. That means the heavier actinide will form a stronger complex compared to the lighter actinide. So this is what will be discussed in subsequent part of this lecture. So actinide also, the ionic species, as I will be discussing, there are a different type of species. Now, considering that the actinides have the oxidation state, say from +3 to +6, these are the very commonly available oxidation state of the actinides. Then you can see that if it is a +6 oxidation state, will form a definitely stronger complex than the +5 oxidation state, which will form into a stronger complex with the +4 oxidation state, which will form a stronger complexation than the +3 oxidation state. However, the actinides +6 oxidation state and actinide in the +5 oxidation state, they are extremely reactive in water, and they don't exist at the plus 6 oxidation state, the actinide plus 6, but they exist as the actinyl ion, that is ANO2 2 plus. Similarly, AN5 plus ion also in water medium, it is hydrolyzed and it is forming the species like ANO2 plus. So these are the ionic species for the plus 6 oxidation state, that is the ANO2 2 plus, and the plus 5 oxidation state, that is the ANO2 plus. As will be discussed in subsequent lectures, the charge and the plus 6 oxidation state, this actinyl ion, is little more than 3 plus, and that of the plus 5 oxidation state actinyl ion, that is ANO2 plus, is little higher than plus 2. That means the observed reactivity while forming the complexes for the actinyl ion in the plus 6 oxidation state will be little lower than that of the plus 4 actinide ion, and it will be somewhat higher than that of the plus 3 oxidation. Similarly, the actinyl ion in the plus 5 oxidation state, that is ANO2 plus, will have somewhat higher reactivity compared to the plus 2 oxidation state and somewhat lower reactivity than the plus 3 oxidation state. So the complexation activity of the actinides will be discussed in a subsequent lecture. So before that, we'll be discussing the general chemistry of the actinides. The right side figure gives a comparison of the plus 3, plus 4, as well as plus 5 oxidation states of the actinides, and it shows the ionic radii in picometer vis-a-vis the atomic number of the actinides. And as can be seen, this ionic radii is continuously decreasing for the plus 3 oxidation state and plus 4 oxidation state also. For plus 5 oxidation state also, we see again some relatively less steep decrease, but nevertheless there is decrease in the ionic side, ionic radius. Now coming to the different ionic species of the actinides, as I have mentioned in the previous slide, the lower oxidation states such as plus 3, plus 4, and plus 2. So there is relatively less hydrolysis in the water medium, and the actinide ions exist in those charged states. You can see, for example, americium 3 plus, plutonium 4 plus, and nobelium 2 plus. So these are existing in these plus 3, plus 4, and plus 2 oxidation charged species in the aqueous medium. On the other hand, the higher oxidation states show the formation of the oxo species as shown below. The MO2 plus and MO2 2 plus exist as symmetrical, nearly linear structure where the MO bond order is around 2 for the bond length of around 1.7 between the metal ion and the oxygen. And when due to complexation, MO bond order is lowered, that is, if it is around 1.25, for the bond length is also elongated, and we have 1.95 angstrom as the MO bond length. This ionic species like M3 plus gets oxidized to M4 plus. Similarly, MO2 plus gets oxidized to MO2 2 plus, and these couples are reversible and are fast reactions are possible. On the other hand, the M4 plus to MO2 plus, that is the tetravalent actinide to the pentavalent actinide couple, is slow and it is not reversible. This is because of the bond formation between the metal and the oxygen, and this is a slow process, and that is why this is not reversible couple. For protactinium 5, though one can predict species like PaO2 plus similar to that of neptunium pentavalent or plutonium pentavalent species, but the reported species is PaOOH twice plus. So this is the actual species which is existing, has been reported in the aqueous medium. Plutonium in the +7 oxidation state is not stable in the normal acidic aqueous medium and is stable only in the alkaline medium, the species being MO5 3-. All these actinide ions, they have different colors if taken in appreciable concentrations, and I have given a table here where you can see the color of the actinides. For example, uranium in the +3 state, it is red color. Uranium is the +4 state, is the green color. Uranium in +5 state is colorless, and uranium in +6 state is the well-known yellow color, which we see most of the uranyl compounds in yellow color. Neptunium +3 state is a blue purple. In +4 state it is yellow green. +5 state, that is MO2 plus, that is neptunium O2 plus, this is a green color. NpO2 2 plus, this species neptunium 6 oxidation state, it is pink red, and the anionic species of neptunium 7, that is NpO5 3- in alkaline medium, is dark green color. Same also for plutonium in the +7 oxidation state, there also we get the anionic species PuO5 3-, and also we get a dark green color similar to the neptunium +7 oxidation state. But generally we don't deal with the alkaline medium, the nuclear fuel cycle. That is why these are only academic interest for the neptunium and plutonium +7. On the other hand, the other oxidation states are of great relevance. For example, for plutonium, mostly plutonium 3+, that is color of blue to violet color. Plutonium 4+, it has a tan orange to brown color. Plutonium 5, that is PuO2+, it has a reddish purple color. And plutonium 6, that is PuO2 2+, it has a yellow orange color. So these are the ionic species of plutonium. And americium has mostly americium 3+ as the ionic species, that is having a color of pink or yellow colors depending on the medium. Americium 4+ can also be obtained, and it has a red brown color. Americium 5+ can be done by electrochemical oxidation of americium, and it has a yellow color. And americium 6, that is AmO2 2+, has a rum color in aqueous solution. Curium exists in +3 oxidation state, and it has a pale green color. Berkelium +3 oxidation state in a green color. Berkelium is also existing in +4 oxidation state, and it has yellow color. Californium has a green color. I am covering only up to this because other actinides are produced at a very low concentration, so we will not be dealing with it. I summarize some of the chemistry of these early actinides, that chemistry of uranium. As mentioned in the previous slide, uranium exists in oxidation state +3 to +6, but the +6 oxidation state is most common, that is UO2 2+ ionic species being the most stable, and we are dealing with in our chemistry labs uranium in the +6 oxidation state. Uranium 3+ is a very strong reducing agent because it is not at all stable, and in view of its soft nature, it can form organometallic compounds that, like with ligands like cyclopentadienyl and this UCP whole thrice. This type of complexes are reported for uranium. Uranium 4+ is obtained by reducing uranium 6 oxidation state, that is uranyl ion, by passing this yellow uranyl ion solution through a zinc amalgam column, and it produces the dark green uranium 4 as it is shown in this. Now this uranium 4 also forms the cyclopentadienyl complex, and the structure is given here, where you have the 4 cyclopentadienyl ligand coordinating to the uranium +4 species, and this can be reduced to give this uranium Cp3, that is the cyclopentadienyl complex of the uranium +3 oxidation state. These organometallic compounds are very, very unstable in air, and you have to take special precaution to preserve them. As I mentioned, uranium plus 6 oxidation state, that is UO2 2 plus, is the most stable oxidation state of uranium. And in this case, you are having actually uranium with 2 axial oxygens, and there is equatorial plane which is available for the coordination by the ligand atoms. So complexation of uranium ion in solution will be discussed in a subsequent lecture. I have shown here the spectra of the uranyl ion. See, generally you get this type of pattern where you have the different bands are there, and at appreciable concentration of uranium, this can be used for estimation of uranium. But if the low concentration of uranium is there, then we have to go for different methods by spectrophotometry. What we can do is we can use a coloring agent, and then we can measure the optical density to find out the concentration of uranium ion. Uranyl ion gets hydrolyzed in aqueous medium. The pH is around 4 to 6. That region also gets hydrolyzed, and at higher pH values, it forms dimeric or polymeric species. I have shown this speciation diagram of uranium. You can see here that up to pH 4, uranyl ion is stable, and at increasing pH values, you have the other species like UO2 OH plus, UO2 OH2, which is a neutral species, and also you have subsequently you have this dimeric and polymeric species at higher pH values. Now coming to the chemistry of neptunium. Neptunium has the electronic configuration, as I mentioned, is 5F4, 6D1, and 7S2. So as per this, if all valence electrons are removed, then you can have neptunium 7 plus 7 species, which is an anionic species I have just discussed in the previous slide. And such species are present in alkaline medium. On the other hand, you can also have neptunium in the plus 4, plus 3, little less stable, and plus 5 and plus 6 oxidation state. As I've already mentioned, neptunium is the first trans-uranium element discovered by the reaction of 238 uranium, the neutron capture giving uranium 239, which undergoes beta decay to produce 239 neptunium. This is how we get this neptunium 239 in the reactor, and this is used in the laboratory studies. A very good quality tracer is obtained. Other important isotopes are neptunium 237. 237 neptunium particularly is very important because it has a very long half-life. Now in the radioactive waste management, this neptunium 237 has to be necessarily separated. Otherwise, the waste has to be kept under the geological repository, and the surveillance period will be very, very long. That I will be discussing in a separate lecture. This neptunium 239, as I mentioned, it has the application that it decays to give plutonium 239, which has a lot of relevance because it's a fissile isotope of plutonium. Now in the nuclear reactor, you can get 237 by these two reactions mentioned here. 235 uranium we can get, as well as from 238 uranium we can get by capture of fast neutrons for the 238 uranium, and also by capture of thermal neutron you can get it for 235 uranium, and we get the 237 uranium for the 235 uranium, which undergoes beta decay to give 237 neptunium. Similarly, for the 238 uranium, capture of fast neutron gives 239 uranium, and it emits 2 neutron to become 237 uranium, which undergoes beta decay to give the 237 neptunium. Also, the decay product of 241 americium by alpha decay can give 237 neptunium. So these are the sources of 237 neptunium. And the separation of this neptunium, as I mentioned, it is required for this radioactive waste management purposes. And while doing this valency state of neptunium has to be adjusted so that its separation can be done by solvent extraction or ion exchange type of methods. Neptunium can be converted to the +4 valency by ferrous sulfamate. Neptunium can be oxidized to the +6 oxidation state by dichromate. And this neptunium +4 and +6, these two ionic species are possible to extract using 30% TBP in a non-polar diluent like odorless kerosene or dodecane. And I've shown this figure here, the right side, where you see the neptunium 4, how it is extracted as a function of the nitric acid concentration, and neptunium 6 extraction also is given. So at lower nitric acid concentration, neptunium 6 extraction is higher, and at higher nitric acid concentration, neptunium 4 extraction is higher. So neptunium 4 and 6 can be selectively separated from nitric acid solution by 30% TBP and tuning the nitric acid concentration. On the contrary, if you see the neptunium 5 extraction, it's much less, because neptunium 5 ionic potential is much lower, and also it has charge little higher than that of +2. That is why the interaction with PBP is less. Neptunium 5, it is very important for carrying out a lot of studies in the environment. The environmental chemistry of neptunium is mostly focused on the neptunium 5, that is NpO2+, which is very mobile in the environmental conditions. And a lot of studies in the laboratory can be carried out using NpO2+, which is prepared by using sodium nitrite or even by Fe3. Now this neptunium TBP, whatever I have shown the extraction, it forms this extraction equilibrium is operative. That means one neptunium 4+ ion with 4 nitrate ions and 2 TBP. This is neptunium 4 is in the aqueous phase. The nitrate ions are also in the aqueous phase. The TBP is in the organic phase, and this species neptunium NO3 4 times and 2 TBP, this goes to the organic phase. So that is how the extraction is done. Now this how it is detected, because if it is converted to neptunium 4+, then we can detect by spectrophotometry. There are very characteristic peaks of neptunium 4+, and this is at one peak is there at 704 nanometer as shown in this extreme left table, and another peak is there at 961 nanometer. So these are the two peaks characteristic of neptunium 4+, and then as shown that profile of this neptunium 4 extraction is shown as a function of nitric acid concentration, and this extract, if it is UV visible spectrophotometry is done, then you get the 704 nanometer peak is slightly shifted to 703 nanometer, and this suggests that neptunium 4 is present in the organic phase. Neptunium 4 is relatively weaker acid as compared to both uranium 4 and plutonium 4. Hence, the hydrolysis chance of neptunium 4+ ion in the aqueous medium is relatively lower, and you can find neptunium 4+ being stable even at 0.1 molar nitric acid. But if you go to lower nitric acid concentration, it gets hydrolyzed. For example, at 0.01 molar nitric acid concentration, neptunium 4+ gets hydrolyzed, hydroxylase. On the other hand, if you want to work with the plutonium 4 and uranium 4 ions, that is Pu4+ and U4+ ions, then 0.1 molar nitric acid also they get hydrolyzed. So for a safer side, we go for 0.5 molar nitric acid to carry out the studies of uranium 4+ and Pu4. Continuing the chemistry of neptunium, as I have already mentioned, neptunium, the interest is in the neptunium ion that in the +5 oxidation state, which is also the most stable oxidation state of neptunium. and plus 5 and plus 6 oxidation states, they are forming diisocations. Plus 7 oxidation state actually only in the basic medium. And neptunium ions, they are actually undergoing disproportionation. That is, as I have shown here, 2 neptunium 5 plus ions in the presence of strong acid conditions, they disproportionate, one of them becoming neptunium 4 plus ion and the second ion is becoming neptunium 6 plus ion, and that is how this disproportionation reaction is taking place. It has an equilibrium constant of minus 6.72. This is a slow kinetics of this disproportion reaction due to the neptunium O bond formation and breaking. Both cases, one case actually we are finding this, one of the NpO2 plus ion is getting converted to NpO2 2 plus. So this is not a slow process, but the NpO2 plus ion converted to Np4 plus is a slow process because that is the neptunium oxygen bond breaking is involved in this case. Also, there are other disproportionation reactions like neptunium 4 and neptunium 6. They undergoes the simultaneous self-oxidation reduction reaction as the reaction is given here. And this is just the opposite of this equilibrium reaction are given at the top, which is a disproportion reaction of neptunium 5. And at low acidity, that is at higher pH, neptunium 5 is dominant, and we can carry out studies without bothering much about its stability. This is in sharp contrast to the uranium 5 and plutonium 5 species, which readily disproportionate even at low acid solutions. And neptunium hydrolysis strain is neptunium 4 gets easily hydrolyzed, which is higher than that of neptunium 6, that is the neptunium ion, NpO2 2 plus, which is again higher than that of Np3 plus, and which in turn is higher than the NpO2 plus, that is neptunium 5 ion. They follow the ionic potential trend of these ions. This neptunium 3, it is very, very unstable, but it can be made stable at pH 4 to 5 under a very, very special condition. Otherwise, this gets quickly oxidized to neptunium 4 in air. Neptunium 4, as I mentioned, it gets hydrolyzed very easily, and species of the type NpH2O twice OH3 plus, this type of species are formed. Neptunium 5, this hydrolyzed above pH 7 to form species like NpO2 OH whole twice minus, this type of species. Neptunium 6, this is stable only below pH 3 to 4, otherwise it gets hydrolyzed, and neptunium 7 only in the. Now coming to plutonium, it exists plus 3 to plus 7 oxidation states. So there are 5 oxidation states. All these oxidation states can be prepared in the laboratory. Plutonium 3 and plutonium 4 are more stable in acidic solution. Plutonium 5 is stable in near neutral solution, but it disproportionates readily. So therefore, very dilute solutions are favored for plutonium 5. Plutonium 6 is favored in acidic solution. Also, plutonium 7 also is stable only in highly basic medium and strong oxidizing conditions. Plutonium 8 has been reported but not confirmed. Redox potentials, plutonium potentials close to 1 volt for all these plutonium oxidation states. This suggests that plutonium undergoes disproportionation. The reactions are given here. You can see that plutonium 4 plus 3 plutonium 4 plus ions undergo disproportionation, giving 2 plutonium 3 plus ions and 1 plutonium 6, that is PuO2 2 plus ion, and this log K is minus 2.08. Similar also is the case for the plutonium 5 oxidation state, that is PuO2 plus. Again, 3 of those ions under highly acidic conditions, they give rise to plutonium 3 plus and also plutonium 6. Plutonium 5 also can undergo disproportionation to give 1 plutonium 4 plus ion and 1 plutonium 6 plus ion, and this has a slightly lower log K values for this equilibrium, that is 4.29. This suggests that plutonium 4 plus, plutonium 5 plus ions can be, plutonium 5, that is PuO2 plus ions, can be easily undergoing disproportionation under the laboratory conditions. The absorption spectra of plutonium will be taken up in a separate lecture. Hydrolysis of plutonium, plutonium 4 is greater than that of plutonium 6, which is greater than that of plutonium 3, and this follows the ionic potential trend, and plutonium 3 is stable below pH 4, and it is obtained by reducing with hydroxylamine, hydrochloride or hydrogen. Plutonium 4 is stable above 0.5 molar acid, and plutonium 4 is produced by the nitrite ion, usually by NaNO2, which is used, which converts all the plutonium from plus 3 to plus 4 state and also from plus 6 to plus 4 state. So nitrate has a unique role of oxidizing plutonium 3 to plutonium 4 and also reducing plutonium 6 to plutonium 4. And plutonium 6, this production can be done below pH 3 by treatment with hot boiling HClO4 or by oxidation by silver oxide or ozone. Coming to americium, we know this americium oxidation state mostly common is plus 3 oxidation state, and this is based on this electronic configuration 5F7, 7S2. One would expect that americium should be stable in the plus 2 oxidation state as well, because you have the 5F7 electronic configuration. However, americium 2 plus is not commonly existing in the aqueous solutions, and in very rare cases in solids only you can find americium 2 plus. Important isotopes of americium are 241 americium, which has a half-life of 432 years and it is alpha emitter. It also has a characteristic 60 keV gamma ray. Americium 243, it has a half-life of 7370 years. It is used mostly for studies where this radiolysis possibilities are to be lesser than that of americium 241. Source of americium is already discussed, so I will not mention it further. Americium 241, it is used as a neutron source along with beryllium. It is called americium beryllium source. The reaction is given here. Americium separation, it is very, very important so far the radioactive waste management is concerned. It is not so important in the nuclear fuel reprocessing. The extraction equilibrium for americium extraction by TBP is given here, where you have americium 3 plus in the aqueous phase and 3 nitrate again in the aqueous phase, the 3 TBP in the organic phase going to americium nitrate thrice and 3 TBP. This is a species in the organic phase. Under what condition americium can be extracted by TBP? It can be done by using nitrate salts. That means we can have sodium nitrate high concentration without having nitric acid, and then under that condition we can extract americium 3 plus. Coming to the chemistry of americium ionic species, americium is mostly present in the plus 3 oxidation state. Plus 2 oxidation state also is reported using some of the pulse radiolysis studies where americium 2 plus is produced, but it is not very stable. Curium 2 plus and californium 2 plus are also formed in a similar manner. Americium 4 plus is again an unusual oxidation state of americium, and it can be produced by electrolytic oxidation or a strong oxidizing agent like ammonium persulfate, but requires complexation to stabilize. Americium can be oxidized to the plus 5 as well as plus 6 oxidation states, where you get species like AmO2 plus for the plus 5 oxidation state and AmO2 2 plus for the plus 6 oxidation state. And this oxidation of americium to the plus 6 oxidation state is exploited for the separation of americium from curium in a process called SWayam process, which will be discussed in a subsequent lecture. Americium 5, that is AmO2 plus, it disproportionates in the same way as the other actinyl ions like neptunium, uranium, and plutonium in their pentavalent state in aqueous medium they behave. Also, americium 4 plus, it undergoes disproportionation. I have mentioned here. This americium 4 plus 2 H2O giving 2 americium 3 plus and americium O2 2 plus. And as shown in the lower figure, this disproportionation of americium from 6 molar HClO4 is given here, where you find that the profile of americium 5 is slowly decreasing. And after 2 hours, you can see that it becomes almost 1/3, less than 1/3 that we started with. And you have this growing profiles of americium 6 as well as americium 3. Now coming to the chemistry of americium in the trivalent state, it is very similar to that of lanthanides. You'll find that this americium creates a lot of problem in the radioactive waste management because of the similarity to the trivalent lanthanides. So lanthanide actinide separation is one of the very important steps in the radioactive waste management. Also, this americium chemistry is very similar to that of curium, and so it was really very difficult to separate, and that is how Seaborg faced a lot of problem in the separation of the americium and curium when it was being discovered. Then absorption spectra of americium, the strong absorption band they have shown here at 503 nanometer. This is characteristic of americium 3 plus. This is due to the transition to 7F0 to 5L6 transition with an epsilon value of 400. Hydrolysis and complexation of americium will be taken up in a subsequent lecture.